here's a question. How many times, shouldn't be any more time, how many times can you fold a single piece of paper in half? And I want multiple guesses. I think some of you might already have some, but okay, Rima, you say 7. Some people say 6. Okay, we have 6. Okay, what other ideas? We heard 7. What about you? You say 7? You say 8? We're going to put it like this. Over here? 12? We have 12? Hey, who knows? Over here, Xander? You say 13? Any other ideas? Yes? 4. I don't know that one. I know that's a joke, but I don't know it. Will. I'm not going to put that. So we have some guesses. So now what I want you guys to do is to fold it in half as many times as you can. No, just in half. Half every time. Your fold should be just in half every time. You got 6 full ones? It's rough. Is anyone at 7 yet? Did anyone get to 7? Over here, Raj. You got to 7? I got it. Oh. Okay. Wow. You have 8? Holy cow. Okay. Let's take a look. You got 7? Wow. Oh. I guess, I don't know. I haven't done it that way. People just hold it in half at a time. Oh, you guys got this in one way, I just hear some paper crackling. But that's so interesting. What happened? Why couldn't we get to 12? Or 13? Rima, what do you think? There's too much tension? Yeah, there's like so hard to fold and it's so thick. Like suddenly it just becomes really, really hard to bend. So in my hand, I have the one I did. I only got to 6. Or maybe this is 5, I don't know. Then we have, was it Viraj, who did get to 7s, but I do notice that it's like, it's not perfectly folded, right? It's still not perfectly even. And then I have Ivy over here who says she got to 8, but it also isn't quite perfectly square, right? It's not like it can be the exact perfect number. Okay, so this is interesting. Does anyone know what kind of function this represents? So we just did, Charlie? Exponential. Why do you say exponential? Yes, exactly. We're doubling the width of the paper every time you fold it in half. So that's great. Interesting. Okay. So I looked online to understand this. Paper thickness is about 0.1 millimeters long. So it's very, very thin. So if I was to express this as a function, I know my 0.1 would be represented as my A in this case. But what number am I focusing on here? What's happening every time that we said well, are we halving it or are we doubling it? We're doubling it. So in this case, I put a 2. I'm writing this nice and big so you guys can see. But we're not going to add it to anything because you just start at 0 folds. So how many folds could we make? Like how many do you think we could confidently make every time? I feel 6 was the most common one. I'd say 6. You guys are so funny. So, if I was to graph this on here, it's like, oh, well, if we didn't fold it yet, we already know the paper thickness is at 0.1, but then after we do it once, it's at 0.2, after we do it a second time, 0.4. You guys have seen this already. You kind of know what the exponential graph, I know it's not perfect, but you know what it's going to look like, right? But it's like we could almost get to 7. Like some of us almost got there, but didn't fully, right? So what if I didn't make it to, it's really small, but what if I didn't make it to 7 folds, but I wanted to represent that with my exponential function? So I'm just drawing this. I want you guys to just pay attention because this will help you with everything else we're doing today. So I know I started all the way down here. I'm going to plot right here because that was my starting point. Let's say this is 1, 2, 3, 4, 5, 6. Say this is 6 folds. And say this is also 7 folds. Yes, 7 does come after 6, but we don't need to look. So in this case, I'm not going to write a number over here just for now. I'm just going to put a little hole. I'm going to draw this little section. Who thinks they know why I drew a little, oh my gosh, I drew a little hole where 7 is? Asha, why do you think I drew that? Because it goes close, but it never reaches it. So it's almost like you folded a paper 6 times, and you're like at 6.7, almost to 7 folds, but you're not quite there. So this is meant to represent what we're going to be doing with domain and range, where it's like it almost reached 7, but it didn't include it. That's what our whole is going to represent, that it doesn't include a specific number. But we know it gets very close to it. But if I drew a dot here instead, what would change? We reached 7. 7 is suddenly included in our domain. So, you can go ahead and get rid of that paper. Just put it off to the side. Shouldn't be a distraction anymore today. Here's an interesting question. Theoretically, how many folds would it take to get us to the moon? What an interesting question. Okay, we have one guess. Over here? 42. 42? Over here?
41.
41? That's so funny. Any other guesses that aren't the common jokey numbers? Commander? 1,200? I'm going to start writing these down. 1,200. We had 41. We had 42. We had... Over here, Will.
Like how you have 1 cent, we double it after
Jimmy?
Could be.
Okay. You guys are just, 40? Okay, we're going to come back together. I wanted to get something different than our normal. I know, it's kind of fun to talk about, right? We have a lot of different ideas. 100? Okay. So interestingly enough, we're going to move on. Interestingly enough, whenever you fold your paper, theoretically, I know we couldn't get past 7, but if you could, that's the cool thing about math. You can make calculations as if we could do things that we physically could not be able to do. It would only take 42 folds to get you all the way to the moon. That's because the paper thickness doubles every single time you fold it in half, and it will skyrocket all the way to the moon. Don't worry, I checked out the math. It's actually quite a popular question to ask. It's so interesting. You wouldn't think it takes only 42, but it does. So just theoretically, paper folding. Who knew, right? Okay. So we're going to move on to our notes. As you guys are already well accustomed to. All right, this one is not in the blue packet, but it'll help you understand your blue packet better. I think I'd be better at passing the paper. Can we say it out loud? What kind of function is it? A quadratic. That's right, because we have a parabola. Parabola is always going to be that happy U or a sad U. I see it as a smiley face. Makes math a little more fun. So, we need to look at what the domain would be in this case. Now remember, our domain is all the x values that are in this function. Ooh, I hear some no's, but that's the range. Okay, so Jimmy already said it's all real numbers above -6. Does it include -6? It does, yes. So that would be our range, all real numbers that are greater than or equal to -6. That's because we see it passes through -6. There's no hole there, so we know it does include it. So in this case, what would be our x values? All real numbers? That's because it's forever going left and right. So it would be all real numbers. Okay. So we've already practiced that a little bit. You're familiar with it. Jimmy did an excellent job pointing out the range. So we're going to talk a little bit more about minimum and maximum that we introduced last week. So we're also going to learn a new way of writing our domain and range. Because it's kind of annoying to write all real numbers less than or equal to 6. Like putting that just in normal words can kind of be annoying. It's a lot. So there's a shortcut to do it. So we're going to introduce that today. So the first step to writing in this new way for our domain and range is we have to identify the minimum and the maximum values that our independent and dependent quantities can be. So, notice there is a hole on this graph. We kind of went over what that means, right? It's like it almost gets there, but it doesn't quite include that last number. So, when we're looking at it, does it look like we include -4 when we're looking at our x values? Use some yeses. It's just a black dot. There's no hole. So we know our minimum value here. Ooh, I'm gonna sorry, I'm a little slow with this other one. All right, so our minimum, IQ minimum, is indeed -4. And the maximum value it reaches, it does indeed reach -6, but does it include it in its domain? That's the difference. So we will say that our max for it is indeed 6. That's just the maximum value that the graph reaches. But it'll be a little different with our domain and range. So when we're looking at our dependent quantity, I'll do that one in green, because why not? Our dependent quantity, it reaches, wow, Asher is on it today. Asher said it reaches -2, which kind of can be a little hard to see. It goes all the way down here. That's where it touches. Does someone think they know what the max is in this case? I know, Asher, you've got it. Can I hear from someone else on this side of the room? Who thinks they know what the max is? Lauren. What is it? There is no max. Oh, because the n is there, right? So that might be a little confusing. In this case, it does reach up to +5, but it just doesn't include it in its range. So we're going to look at it just as what the number is. Our max is indeed 5. It is included in our minimum and maximum. But that is a great point for our range, that suddenly it'll be a little different. We're going to draw it a little different. So the next steps would be to determine whether these values are included or not included, which is what we've been looking at with the whole. So under where it says number 3, I want you guys to write domain and then range. I'm going to break down what this would look like. So earlier we said when we're looking at the domain, it goes all the way to -4 and it's a filled in dot. So we know it's included. So let's go ahead and just put -4 to start us off, because that's where it starts. And because it's included, we're gonna put this little sign here that says less than or equal to. I'm gonna put a value of x after that. Does it include +6? Say it out loud. Yes or no? Does it include +6? No. See a lot of yes as well. So in this case, because there's a hole, it doesn't include it. But we know it reaches towards it. So I'm going to put just a less than symbol. I'm not going to put the equal sign underneath it. And then a +6 on the other side. Interesting, right? Have you guys seen this before? Maybe some people have, some people haven't. It's a little weird, right? Like, it's like, what value could our x be? Well, I just want you to think of this as an inequality sandwich, right? Our x is the meat stuff. That's the stuff we want. That's what we don't exactly know what it is. But the value of x can be anything between -4 and 6. But it could also be -4 because we have that equal sign. Less than or equal to -4. Can x be 6? No, it can't, because we don't have the equal sign under it. It doesn't quite get to 6. But we know our x value could be anything on that black line, or it could be that black dot, but it cannot be the hole that's on the top. So, for our range, in this case, indeed, Asher, maybe you should teach instead of me. You've got it. We've got -2 is where we started, right? And it is indeed a black dot. So it would still be that less than or equal to sign. But I'm not going to use x this time. What value have we been using for function notation for y? We've been using f of x, right? So that's what we're going to put instead for range. We're going to put f of x. Let me write it. Does it reach 5? Yes or no? Or does it include 5? That's the better word. Does it include 5? No. It reaches it, because we've talked about that with the maximum. But it doesn't include it. So again, we would just put the less than sign of 5. Awesome job. Okay. So we know our y values, or the answers, could be anything from -2 to anything a little under 5. So could it be 4.9? Yes, it could be 4.9. Oh, you guys are like, it's Monday. But thank you guys. It can be anything right under 5. Let's go ahead and move on. And then we'll do something a little more interactive instead of just notes. So I think you guys will enjoy it. We'll go fast. All right. So on the other side,